In this video, I am just going to quickly run through some of the weaknesses of the spontaneous collapse theories. And probably one of the more glaring ones in my eyes is that the GRW theory must posit these two new constants of nature, namely the sigma equals 10 to the negative 7 meters and the lambda equals 10 to the negative 16 collapses per second. And so this is just sort of, like I said in a previous video, based on phenomenological considerations. And so they're essentially just posited as being things that will make the theory actually agree with observations. And so in that sense, they're not really derived from anything. And so to me, that seems like kind of a weakness of it. And especially if you read the literature on it, not everybody even agrees on what these parameters ought to be. But more than that, the two primary types of ontologies discussed, so the matter density field and the flash ontology, both commit us to thinking that we live in a very strange world. So in GRWM, in the matter density field, we are committed to believing that we live in a world where matter is sort of smeared out in space. This is mostly within a range of around 10 to the negative 7 meters. However, it is also in some way that is not quite clear, extending off indefinitely in all directions. This is said to be quote unquote low density matter, but what does it even mean for matter to be low density? So it's not really something you can interact with, and so what does it even mean for it to be low density? And so we get into things like the problem of tails and things like that. And then in the flash ontology, we are committed to believing that things do not exist in the real 3D world most of the time, but only as flashes based on whatever is happening in some ontologically separate configuration space. So because of these parameters, our lambda and our sigma here, we also are committed to the fact that smaller things spend even more time existing only in this strange configuration space than larger things. And indeed, in a footnote in another paper authored by Allery et al. In 2007, says this: an anonymous referee, so somebody who was peer reviewing this paper, has remarked that according to the flash ontology with the original parameters in a single living cell, there might occur as few as one flash per hour, so that the cell is empty of matter for surprisingly long periods, quite against their intuition of a cell as a rather classical object. We make a few remarks to this objection. First, one should of course be careful with the language here. There is presumably no cell in the flash ontology, though the structure of the wave function on configuration space, even though there are no configurations, might suggest otherwise. Second, it all depends on the choice of the parameters. So again, this is that thing where I was saying that it's not even agreed upon what these parameters are. So it all depends on the choice of the parameters, and as long as experiments have not fixed their values, this cell argument may indeed be an argument for a choice different from GRW's original one, say with a larger lambda or larger sigma. We do not wish to argue here for any particular choice. Third, while most people might expect a cell to be real in the same way that a cat is, one would not necessarily expect this of a single atom. Thus, it seems quite conceivable that, at some critical scale between that of atoms and that of cats, the ontological character of objects changes, as indeed it does in the GRWF, because of the limited resolution of matter given by the space-time density of flashes. For example, in water, approximately one flash every 20 micrometers every second. The cell example shows that the critical scale of GRWF is larger than one might have expected, and thus that GRWF is a mildly quirky picture of the world. But this mild quirkiness should be seen in perspective. In comparison, many other views about quantum reality are heavily eccentric, as they propose that reality is radically different from what we normally think it is. For example, that there exist parallel worlds, which is probably talking about the many worlds interpretation, or that there exists no matter at all, or that reality is contradictory to itself. And so this I thought was curious. So they say in this footnote that the anonymous referee said that a single living cell there might occur as few as one flash per hour. And that actually got me curious about where that number might have come from. And so I actually ran some rough calculations here. I have them in purple here. I'm not going to go through the calculations in detail. I'll kind of skip here to the punchlines. So if I just look at the number of atoms in a cell, so for a eukaryotic or prokaryotic cell, there is about 200 nanoseconds between localizations for the eukaryotic cell and about 30 milliseconds between localizations in the prokaryotic cell. So that is a lot more than the once per hour that that anonymous referee said. And so I tried to look at maybe if we talk about instead of the constituents of atoms. So in this one, I was looking at actually splitting up between protons, neutrons, and electrons. I thought, what if we looked at the molecules? Because the atoms in molecules are going to be entangled with each other. So if we just look at this for molecules, what I actually find is that we still have one collapse every 10 milliseconds, so about 10,000 flashes per second in a eukaryotic cell. If we take the prokaryotic cell to again be about 3 orders of magnitude longer between flashes, we get 0.1 seconds, meaning that the prokaryotic cell has a flash about 10 times per second. So while this is still bizarre, saying that the prokaryotic cell only exists about 10 times each second for these little flashes of time each second. So while that's bizarre, it is certainly not the once per hour that the anonymous reviewer said in the footnote. So I'm actually still not sure where that number comes from. But anyway, that was my analysis of it. It's still, like I said, somewhat bizarre that we have to commit ourselves to thinking that most things don't actually exist most of the time, only these little flashes every split second, and so we have a sort of discrete existence in time. So some other weaknesses here. So one weakness of the GRW theory is that it may violate conservation of energy. So this is due to the Brownian-like motion of the particles, so they're constantly collapsing and flashing or even sort of just moving, sloshing back and forth as a matter density field in regions that are mostly within this somewhat small but still finite area. So the particles are therefore constantly undergoing accelerations. To combat this, though, there have been dissipative models that have been proposed for us. So you can check out these papers if you want to look into that. However, this Brownian motion does make the prediction that charged particles will emit a very low-level electromagnetic radiation because they are constantly undergoing these accelerations. This has specifically been tested in experiments looking at the Diauchy-Penrose model. For instance, this paper here from 2021 tested this and found the following. So this figure right here is going to be described here. So they're looking at the lower bounds on the spatial cutoff of this R naught, which is the length of the mass distribution of the nuclei for the Diauchy-Penrose model. According to Penrose, the value of this R naught is estimated to be the size of the wave function of the nuclei of the system, which here amounts to about 0.05 times 10 to the negative 10 meters for this right here, which is the germanium atom. So that's what they're looking at right here. So for the germanium crystal used in the experiment. So our experiment sets a lower bound on the R naught at 0.54 times 10 to the negative 10 meters. So that's this right here. And this is 1 order of magnitude larger than what was predicted by Penrose's argument. Therefore, this parameter-free version of the DP model is excluded. So the figure up here shows also previous lower bounds in the literature based on the monitoring of Brownian-like diffusion predicted in this model. They refer to data analysis from gravitational wave detectors, so that is the red bar and arrow up here, and neutron stars, which is this blue arrow right here. Then later in the actual text of this paper, they say, our experiment sets a lower bound on the R sub naught on the order of 1 angstrom, which is about 3 orders of magnitude stronger than the previous bounds in the literature. So they're talking about the neutron star and gravitational wave detector bounds. If R sub naught is the size of the nucleus's wave function, as suggested by Penrose, we would have to confront our results with known properties of nuclei in matter. In a crystal, the r sub naught is equal to this, where the u squared here is the mean square displacement of a nucleus in the lattice, which can be computed by using this relation here. And that's the Debye-Waller factor for the germanium crystal, cooled down to liquid nitrogen temperature. One obtains r sub naught equals 0.05 times 10 to the negative 10 meters, which is more than 1 order of magnitude smaller than the lower limit set by our experiment. Therefore, we conclude that Penrose's proposal for a gravity-related collapse of the wave function in the present formulation is ruled out. And so, being falsified by experiment certainly counts as a weakness to the theory. All right, so additionally, I've already discussed some of the other issues that are often brought up, namely issues with making the theory relativistic. So you can watch the video on that, and the problem of tails in the GRWM theory. So you can watch my video on that. So since I've already discussed these issues, I will not go into a whole lot of detail on these, but I will make the following comments. So making GRW and the Flash ontology in particular relativistic ended up with a trade-off, where making the theory respect relativistic space-time structures caused it to become super non-local, and that we lost any meaning given to cause and effect. So what I mean by that is it becomes symmetric, and so we cannot distinguish between what was the cause and what was the effect. And then there is the problem of tails in the GRWM, so the matter density field ontology. And so as discussed in that video, this leads to a sort of apocalyptic many worlds interpretation, where anyone unfortunate enough to find themselves in the tail worlds are promptly exterminated by radiation. This is an even more radical claim than the canonical many worlds interpretations. It also touches on why we don't seem to find ourselves in such inhospitable worlds, which could have to do with what is called quantum immortality. That is something I will discuss in the future when I get to the actual many worlds interpretation proper. But anyway, these, like I said, are just some of the weaknesses that we see in this theory of quantum mechanics. But I hope you found that interesting, and I will see you in the next one.